All right, everybody, how we doing? So we're actually finalizing our last chunk of notes here and slides here for this chapter. I know it's crazy. It's only been three of these videos, but we're already pretty much done with chapter 9 here. So we're going to finalize it all today. There's really two topics today, but one bigger topic that we're going to cover towards the end of this video here. This first one here is talking about electromagnetic radiation, and it's a type of energy that just travels through space. Right? There's tons of different types of energy that we'll see on the next slide here, but this one travels through space and travels at a very, very specific and accurate speed, right? And that speed is also known as the speed of light, and that is measured at 3.0 times 10 to the 8th meters per second. And what that actually looks like as a full number, right? Because if you remember how to transition from scientific notation to standard notation, this number here actually would look a little something like this. So 3.0 times 10 to the 8th is actually 3 with 1, 2, 3, 4, 5, 6, 7. I think we go 1, 2, 3, 4, 5, 6, 7. One more 0. There you go. 3. So we've got here, comma here, 300 million meters per second. 300 million meters per second. Okay, that is the speed at which light travels. So pretty fast. And so what this actually does is it allows scientists to actually describe energy as either two things, particle or wave. This is a concept known as wave-particle duality. It's something that I learned a lot about in college, but you guys don't actually have to learn a lot about right here in this class. It's pretty crazy stuff. Gets into that whole quantum chemistry stuff that I was telling you guys about a few weeks ago that is like kind of like way out of the scope of this class. But we do have a couple of things that I do want to talk about and have you guys learn about this stuff. So more importantly, what this stuff totally means is that electrons can absorb or emit energy along this electromagnetic spectrum. And that's really the main crux of what we're talking about, this electromagnetic spectrum, which is this right here, okay? You guys might have seen this maybe in middle school by chance, okay? But this whole stretch here is the electromagnetic spectrum. From the left-hand side with the lowest energy are things like radio waves, going towards microwaves, then infrared radiation, okay, some of you guys might be familiar with. And then this small little sliver right here in the middle here is the visible light spectrum. It's the spectrum that we are able to visually see with our eyes, right? All the different colors that you guys are able to normally see on a day-to-day basis come from that small little sliver right there, the visible light spectrum. Then outside of that is the ultraviolet radiation, X-rays, and then all the way at the highest energy on the right-hand side is our gamma rays. Okay, and those are the most dangerous of them all as well. Okay, and this whole stretch of electromagnetic spectrum is truly just characterized by its wavelength. Okay, by its wavelength. This would be a normal picture, right? This is just some random guy with his dogs. Okay, and then if you were to change the lens on that camera, okay, to change it from, instead of it being the visible light spectrum that this picture is shown in, you can actually change the lens to have it show the infrared radiation spectrum. Okay, so infrared radiation is this one right here. Okay, there are some similarities in the color you can actually see with infrared radiation and infrared lens. So let's take a look at that next slide here and see what it looks like when you change that lens. Okay, so normal photograph, compare that with infrared photography, right? You might be like comparing this to something like a heat lens, right? Maybe you guys playing video games, right? You put the little infrared goggles on, right? And this is kind of what you see, right? It's like heat signatures. What's kind of what infrared radiation is based on, right? It picks up heat signatures and helps us to kind of identify things that way in a totally different kind of color scheme, right? So that's infrared photography. Now, this idea of energy, right? Because at the end of the day, especially when we talk about Bohr models here, we talked about the excited state in class earlier today, right? We focused some of our efforts on talking about the excited state, being able to identify configurations that were in the excited state or the ground state or not possible. Well, how does an electron become excited, okay? Well, it's very, very simple, okay? Electrons can just absorb or emit energy. When they absorb energy, they enter the state called excitation, right? And excitation is right here, okay? Enters this state of what's known as excitation, okay? And when that happens, guys, what happens is the electron moves up in energy level. And when I say energy level, what I mean is PEL, right? Our principal energy levels that we've been talking about with these Bohr models, right? So let's say, for example, okay, here is the first principal energy level. Here's the second one. Let's talk about maybe our third one here, okay? Our third principal energy level. So I'm gonna put a dot right here, okay? One of our electrons, okay? So what happens here is our electron can move up to a higher energy level and go to, let's say, the fifth principal energy level right here. And I actually adjust the color so you can see the difference here, okay? Let's change the color. Let's do like purple or something, okay? So now this dot is on the fifth principal energy level and it has moved from the third, okay? This electron has moved from the third up to the fifth. So it's excitation, okay? It moved up in energy level because that electron itself gained energy. Now, what happens sometimes is that after a period of time, that electron will actually want to emit that energy or release the energy. And when that happens, okay, that releasing of energy here is known as relaxation. Okay, where it releases that energy. Okay, and when that happens, that electron will then move down an energy level. And essentially what happens is this. So I will redraw this electron right here. Okay, it's the second purple one right here. And now in relaxation, the same thing kind of happens, okay, but in the reverse direction. So that electron will move from the fifth principal energy level down back to the third principal energy level, okay? So this is all one similar instance here, okay? So when that happens, when that electron that had all this energy went up to a higher state, moved from that higher state back down to that lower energy level, okay, that's called relaxation. And when that happens, it gives off a distinct amount of energy. And when it moves down to that lower energy level, we can actually measure that energy. And that's why it's so distinct, right? We can actually measure that energy. And the really cool thing about that is the sort of releasing of that energy, that measured energy that we can measure is actually measured in the form of light. Okay, so this energy releases results in a distinct emission spectrum, which can be used to identify the element. And that is what we're going to focus on in the next slide here. So the atomic emission spectra, okay, again, it's all, releasing this energy in the form of light, okay, and that's how we're able to see this emission spectra stuff here. So when an electron travels back down from that higher excited state back down to the ground state, it emits energy that I was just talking about in the form of light, okay, and that's how we're able to very, very easily measure it, okay. And this right here is a great example of someone's emission spectrum, and that's someone being hydrogen, okay, our element hydrogen, number 1 on the periodic table, okay. The cool thing about that is that it does it in these small individual little bands here, right? There's 4 different individually colored bands, B-A-N-D-S, bands that you see right here on this emission spectrum, okay? And you can actually identify them just by looking at the band and the actual measurement in nanometers. NM is nanometers. Well, how does this impact you guys? How does this affect you, and how will you use it in the future here? Well, what you guys will be doing is using emission spectra to identify a mixture of elements, right? That's one of the more popular things that ends up happening here. So you've got this thing known as the white light spectrum, okay? That is kind of just like the spectrum of colors that we all see, right? Ranging from red all the way in the far left here, all the way over to the right with purple, okay? That's the visible light spectrum that we can physically see, okay? That always gets compared to all of the individual bands here in the spectra of our individual pieces here. So we've got a band for hydrogen right here, and we've got a band for helium right here. So what we want to do is create a mixture of these two spectra here. And all we do, guys, is we sort of trace down, I'm going to grab my black color here. So we identify each of the bands in these two samples here. So our first sample here is hydrogen. So I'm going to draw an arrow down and say, hey, one of my bands from hydrogen will end up here. One of my bands, okay, my second band of hydrogen will end up here. Third will end up right here. And my fourth will end up right here. Okay, so that takes care of hydrogen. Now let's look at helium. Okay, helium, I'm going to have one band right here. I'm going to have another band of helium right here, because again, we're creating a mixture between hydrogen and helium's bands. Another band of helium right here, and the final band of helium right there. Okay, so now what we get to do is we get to match the color of that particular colored band from hydrogen and from helium. We match the color and we draw it on our mixture of the two right here. So this blank little canvas right here at the bottom, okay, that's going to be our mixture of hydrogen and of helium here. So let's kind of get these colors here. I don't have a red color, but I'm going to do a pink here for our red band of helium right here. So we'll do, it's supposed to be red here. And now we've got an orange band coming from hydrogen right here. Okay, now the next up here is a helium band that is yellow. So we got a yellow band of helium right here. Now the next one is a handful of bluish looking bands from both hydrogen and from helium. So these are some lighter colored blues here. You know what? I actually think I have a cyan color. Yep, I do. So that is a cyan looking color right here. Another one right here. We'll do another one right here, and we'll do a darker blue right here. We'll do an even darker blue for this band. Okay, it's one of the last bands of hydrogen here. And now lastly, we will end with a purple band, which is our very last band of hydrogen. Okay, so that right there, guys, is a mixture of all of the different bands from both hydrogen and of helium. Okay, and that's one whole mixture of both those bands, right? So all we did was essentially transfer the bands from hydrogen and the bands from helium over to one whole strip, right? One whole spectra. Okay, and that's how you kind of identify or create a mixture of elements for an emission spectra.